In today's lesson, we are going to look at error checking methods. We'll find out how an error can be detected in the data packet being transmitted over a network. Alright, let's begin. So, something you should know by now is there's no such thing as a perfect system. Today, we will look at multiple error checking methods. None of these are perfect, as they will all come with their benefits, and more importantly, what we'll focus on is their limitations. So, how do errors occur during transmission? Data packets are carried over a wave. This can often cause bits of data to suddenly flip, especially when there is a data collision. It can cause some binary digits to change. This changes the data completely and now makes it unreadable or incorrect. We need a solution to fix this problem. Luckily, there are quite a few. We're going to look at these in today's lesson. In today's lesson, we're going to look at a few methods for checking for errors in transmission. The methods we're going to look at are called Parity Checking, Automatic Repeat Request, or ARQ, believe it or not, CHECKSUM, and Echo Checking. Let's look at parity checking. But before I explain this, you need to know what is meant by an odd parity and an even parity. It's simple. The parity refers to the number of ones in our data. An even parity means we have an even number of ones. An odd parity means we have an odd number of ones. Parity checking, the data being sent is given an additional bit known as a parity bit. We are supposed to use the parity bit to either create an odd or even parity. In this example, if we want an even parity, we put a 0 as our parity bit, as we already have an even number of ones. But if we want an odd parity, then the parity bit becomes a 1, so we have an odd number of ones. But what does this have to do with error checking? Well, if we know the data should have an even parity after transmission, in theory, we should identify an error occurred because it would have a bit flipped and therefore have an odd parity when it's meant to have an even parity. Really straightforward, really simple to incorporate, so that's why it's so good, because it's not very complicated at all. However, one big limitation of this is, let's say we're going for an even parity, and right here we've got 2 ones and we've got 2 zeros. If we're looking for an even parity and the 2 zeros flipped to ones, we still have an even parity. That is a big issue because it would suggest that no errors have occurred. Next, we will look at automatic repeat request. With this method, once the sender has sent the data, it will wait a set amount of time before it is informed by the receiver that all data has been received. If the receiver does not send its confirmation within the time, the sender will send an automatic request for the confirmation. This will repeat until the receiver confirms it has received. Now we're going to take a look at checksum. Now a checksum is just a value that we calculate based on the data we're about to send. Okay. Now this value is then recalculated by the data that gets received. If the two values are the same, then that means the data has been sent with no errors. But if they are different, that means an error has occurred. But now the question is, how exactly do we calculate a checksum? Let's have a look. The data is often sent out in bytes. To calculate the checksum, we add up all of the bytes. If the number we get here is less than 255, then that's our checksum. Easy. However, if it's not less than or equal to 255, we have to do some more calculations. We first of all take this number and divide it by 256. The answer we get should be rounded down to the nearest whole number. We now multiply this new number by 256, then take this answer away from our original number. The number we are left with is our checksum. Pause the video here to give yourself time to take that all in. Again, feel free to go back. I know I spoke very quickly there. Now, this method is great. However, one problem we could have with this is actually some of the bits in the different bytes could flip. But they could flip in a way that means the checksum actually remains exactly the same, even though the data is different. With that in place, we won't be told there really is an error during the transmission. So that is a big problem with checksum. Alright, now it's time to look at the last one. Echo checking or echo check. This method is pretty straightforward. Once the data is received, the receiver will then send the data back to the sender, or a copy of it back. Okay? This way the sender can compare the data it sent to the data that was received. This way it can check that the data was received with no errors. And that is echo check. Now, as simple as that might be, just as with the others, there is quite a big problem with echo checking. You may have spotted it during that explanation. If you didn't, that's fine, I'm going to explain it now. So, let's imagine the sender is now sending our data. However, halfway through transmission, a bit flips. This is the data that is now received by the destination. Now, obviously, there's a problem there. So this receiver is going to send a copy of this data back. The idea is that it should see an error has occurred. However, what if during the transmission of this data being sent back, that same bit flips? This means the sender now receives the exact same data back, and therefore it will believe the data was sent perfectly, when in actual fact it wasn't. And that is everything you need to know about error checking.